So let's take a look at synthesis reactions. It's the first subtype of the redox reactions that we're going to talk about in more depth. Remember that redox reactions have at least one chemical species that is going to be gaining or an electron or bonds, and the other one's going to be losing them as the electrons are redistributed during these chemical reactions. Now, we had talked briefly in the last video about how each of these subtypes has a key feature or a way to recognize it, and it allows us to make some predictions about what's going to happen. For synthesis reactions, that key feature or the common thread between them is that in all of these types of reactions, we have multiple smaller reactants, and they bond together to form a single larger product compound. Here we have 4 examples written at the bottom. In the first 3, we have a metal atom combining with a nonmetal to make the ionic compound that results between the two. In the last example, we don't have an ionic compound forming. Instead, we have a covalent compound. This is the synthesis of water reaction, but when you have hydrogen reacting with oxygen, as Mark Watney had done in The Martian to make water, that is also a synthesis reaction. These types of reactions tend to release a lot of energy because, as we had talked about earlier in the year, whenever we form a bond or form a link between things, energy is released as they become more stable. And because these things tend to form a lot more bonds than what we're breaking, these types of reactions tend to be exothermic. But we'll look more closely at those stages in a moment. To examine this, we're going to look at the reaction between sodium and chlorine specifically in a little bit more depth. So the first thing we need to do is get from the descriptive sentence that we're using to start down to that model. So just a quick review from the last video. In this sentence, what we see is that we have molten sodium metal reacting with, so that's our plus sign, chlorine gas to form solid sodium chloride. So for my word equation, I know I have sodium metal. That's just the element sodium. And it says that it's molten. And I'm not sure if we're very familiar with that word or not, but molten means melted or liquid. So we have really, really hot melted sodium metal here. We're reacting that with chlorine gas. So the element chlorine in its gaseous state. And it's forming sodium chloride in its solid state. Turning this into a chemical equation, the symbol for sodium is just Na, liquid. Chlorine is Cl, but remember that it's diatomic because it bonds to itself. So Cl2, and it's a gas. And sodium chloride. Sodium has a charge of +1, chlorine is -1, so we just get NaCl. Now this reaction is currently not balanced because we have 2 chlorine atoms here and only 1 on the right. So to balance this out, I would need a 2 and a 2 there. So we have our balanced chemical equation, and this reaction is one that I always found interesting because sodium metal, if we remember from the reactivity of metals lab, is one of those silvery metals that when we put it into water, it burst into flames, eventually sparked and popped, and overall really, really reactive, and obviously not something that you would want to consume in your mouth because that would be happening inside of you. Chlorine gas is a yellow gas that if you breathe it in, the chlorine atoms there will bond with the hydrogen in the water of your lungs to turn the water in your lungs into hydrochloric acid, which will kind of burn you from the inside out. It's a poisonous gas that was actually used as a chemical weapon in World War I. And obviously is very, very, very bad. But here, if we take these 2 really, really unpleasant elements, things that wouldn't be very harmful for you, sodium metal and chlorine gas, if we react them together, we get sodium chloride, which is table salt. And is what we put on our popcorn and french fries and to make them taste really good. So we have this idea that we always need to keep in mind that when we do a chemical reaction, the properties are going to change. It is no longer sodium metal in that product. The sodium metal is the metallic one that goes boom when it hits water, but sodium ions do not. Right? The properties are very, very, very different. So in this reaction, we have a couple different stages that need to happen, and we know that this is a redox reaction. So there is an oxidation, there is reduction. So over the course of this reaction, we know that at the end of this, sodium is going to have a +1 charge, chlorine is going to have a -1. And at the start, both of those 2 things were neutral. So we know that for this reaction to happen, The oxidation step, the oxidation half reaction, was that sodium had to lose an electron, and since there's 2 sodium atoms, it would have to have lost 2 total electrons. Same thing for chlorine. We know that chlorine starts at 0, but it ends at -1. But because there are 2 chlorine atoms, the reduction, what we call half reaction, is that chlorine must have gained 2 electrons from somewhere to become the -1 ion. Overall, we can write this reaction where 2 sodiums form 2 sodium ions and 2 electrons. And if we look at the reduction half reaction, we have 2 chlorines plus 2 electrons form 2 Cl1 minus ions. Now here we have 2 electrons on the product side, we have 2 electrons on the reactant side, so those essentially cancel each other out. And we see our overall reaction here. We have our chlorine and our sodium forming the ionic compound sodium chloride. Before this to happen, there's a couple steps that occur between them. Right? We model the half reactions with the gain and the loss of electrons like we have shown here. But let's look specifically at how these 2 things get together. First, before we do that, let's take a look at the video of this reaction so we can see exactly what it is we're talking about. So here we see Mr. Milam helping us out with the sodium and chlorine reaction again. He took the piece of sodium metal, heated it up so it's molten, it's red hot there. And as he puts it into the chlorine gas, we see this very bright reaction happening. Obviously very exothermic as it's releasing lots of light and heat. It's glowing with that yellow color that, if you remember back to the flame test lab, was very indicative of when we were burning the sodium chloride in the water, making that bright yellow flame, that sodium vapor flame. Now, as this reaction is coming to a close, we see this white smoky dust kind of in the center of the flask. That's actually sodium chloride, that's salt. Right now, the particles are so fine that it's kind of suspended up in the air, but if you let it sit for long enough, all that white film would actually settle back to the bottom of the flask. So, first thing that happens in this reaction. In order for sodium and chlorine to react, sodium has to lose electrons. Now, this is not an easy process because those electrons are attracted to the nucleus of the sodium atom. So energy is going to need to be gained to pull those electrons away. And this is something we've already talked about in this course at the beginning of our distance learning when we talked about ionization energy, because we measured ionization energy as the amount of energy needed to remove the most loosely held electron from an atom. So for sodium to lose its electron, it must gain its ionization energy. So using the link there in the bottom of the slide, I looked up the ionization energy of sodium. It's about 500 kilojoules per mole. Obviously, if we were doing any math, we would use the exact number, but for the sake of our graph right now, I'm just going to make it about 500. So for each sodium atom that has to lose an electron, we're talking 500 kilojoules per mole. And I have 2 sodium atoms that need to do this. So I'm going to need to gain energy of about 1,000 kilojoules per mole. Right, and just for that part to happen. Now, once that step occurs and we've gained that much energy, we have our sodium ions and we have our free electrons. And we know that those electrons are going to be going to the chlorine. Right, so let's go into the next stage, right, stage 2. Stage 2, we have our 2 free electrons, but they can't go to the chlorine yet because right now the chlorine is currently bonded to something else. Right? It's currently bonded to itself to make that molecule of Cl2, our diatomic atom. So before the chlorine atoms can gain those electrons from the sodium, we must sever the bond between the 2 chlorine atoms. Right now they are linked together by the sharing of their electrons. So this bond needs to be broken. And again, anytime we break a bond, energy must be gained, right? Because we are making them a little bit less stable than they were before. We call this amount of energy the bond energy. And every type of bond between any 2 elements, single, double, triple, whether that's carbon and carbon or carbon and oxygen, they all have a measured bond energy available again at that link at the bottom of the slide there. Using that chart, I found the bond energy for the single bond between 2 chlorine atoms, and that's 242 kilojoules per mole. Now, I only have one of these bonds I need to break, so in order to break this, I would need to gain, again, about 250 or so kilojoules per mole. So now at this point, I have 2 sodium ions, 2 free electrons, and my chlorine atoms are separated. So going into stage 3 then, those free chlorine atoms can actually now bond with the free electrons. I'm just adjusting my chart here. This should be 250. So here in stage 3, those 2 chlorine atoms that I just freed up can bond and acquire the free electrons from the sodium. Now, when an electron is gained by an atom, we call that electron affinity, again from back in periodic trends. Now, electron affinity was defined as the amount of energy released when a neutral atom gains an electron in its outer shell. So here we see this number as being positive, right, 348.6, but it's the amount of energy released. We're no longer gaining that energy. So if we're going to put it on our chart, we can actually put it as a negative value because it's going to be going down again, right, as we make our energy diagram here. Now, because I'm going to be having to gain 2 electrons from 2 different chlorine atoms, my total amount of energy here that's going to be released is going to be twice that value. So since this is about 350, I'm going to say that it goes down by about 700. As we gain those electrons. So at this point, I have my separated sodium ions and I have now formed chloride ions, again, separated from each other. So the last thing I need to do is bring those 2 ions together to actually form the crystal lattice rather than these loose free ions. Right? And so that's stage 4, is the actual formation of the crystal lattice. Now this is called the lattice energy for any different ionic compound. Lattice energy is defined as the amount of energy needed to separate the ions. So if I need, in this case, about 800 kilojoules per mole to separate them, then it would release that amount when they come together, right? Law of conservation of energy. So here, when we form 1 unit of sodium chloride, I release about 800 kilojoules, and we are forming 2 units of this. So I'm going to have to release about 1,600 kilojoules per mole. And this was still our typo from before. And as a result, we see that by the time we actually form our sodium chloride compound, compared to when we started with sodium and chlorine, we have an overall loss of energy, right? Meaning that this synthesis reaction is going to be exothermic. We can do the math to figure out exactly how much energy is lost over the course of this reaction by getting the total of the amount gained and the amount lost. And here, using the actual values rather than my rounded methods, we take about all the ionization energies times 2, since we had to ionize 2 different sodium atoms, and the bond energy. And we see that overall, we must have gone up. That's not a pen. We must have gained 1475.6 kilojoules per mole. And at that point, we went down until we got to sodium chloride, because from the peak to the base, we lost 2289.2 kilojoules per mole for an overall decrease, an overall energy of the reaction of negative 813.6 kilojoules per mole. So this red label here is the reaction energy. It's the amount of energy released over the course of the reaction, whereas this value, right, that initial energy that must have been gained, remember back to earlier in the year or biology, is the activation energy, which I misspelled. So here we see over the course of the reaction, we have 4 different stages for this type, where we have the ionization of sodium, we have the bond energy breaking for chlorine, we have the electron affinity for the chlorine gaining those electrons, and then lastly, those things coming together. So for any synthesis of ionic compounds, at least, this is generally the stages that happen. For something like water, instead of ionizing the hydrogen in the beginning, we would have to break the hydrogen bond, and then break the oxygen bond in the oxygen gas, and then have to form some new bonds. Now, it's important to remember that all of these stages that we just outlined for sodium and chlorine, at least, they tend to happen simultaneously, because the electron from the sodium isn't just lost on its own. It has to get pulled off by the chlorine. So as we are pulling off the electron from the sodium, it's also being gained by the chlorine, as the chlorine is breaking its bond from the other chlorine atom. So we use these stages to kind of help us model and think about what's happening, what's processing, but the limitations of these models need to be kept in mind as we work through this.